Now we're going to look at another application, and those are called related rates. Okay, so related rates are problems where two things are changing. So we'll see an example in a minute where we're blowing up a balloon, and there we would have time changing, we would have the volume changing, and the radius of the balloon changing. So we'd have lots of things. So here are the steps when solving a related rates problem. First, we're going to identify all the variables and rates in the problem. So what variables do we have? What's changing? If possible, we're going to make a sketch just to help us figure things out. Then number 3, we're going to determine the equation relating the variables. So this might be a geometric equation. It might be something that's given. Use your sketch to help you. Then we're going to differentiate with respect to time. Now here we're going to have to do implicit differentiation. So for example, if you have a variable that's a radius, you're using r, and you're taking the derivative of that, you would take the derivative like you would for x or something, and then you'll multiply by dr dt, just like we did with y, dy dx in implicit differentiation. So if you had another variable that was volume, when you took the derivative, it would be dv dt. And then lastly, we'll solve for the required rate. So that should be number 5. An important thing to notice is don't plug in any values until after you've taken a derivative. Okay, so we're going to do a problem here. It says, a spherical balloon is being blown up such that its volume increases at the constant rate of 2 feet cubed per minute. Find the rate at which the radius is increasing when it is 3 feet. So that it is the radius is 3 feet. Okay, so we've got a balloon. So we're going to have the volume of the balloon. And that means that dv dt will be the rate at which the volume is changing. And we have the radius of the balloon, so dr dt will be the rate the radius is changing. Now our formula here is going to be the formula for the volume of a sphere, and that volume is 4/3 pi r cubed. Okay, so we're now going to take the derivative of both sides, and anytime we take the derivative of v, we'll multiply by dv dt, and anytime we take the derivative of r, we'll multiply by dr dt. So the derivative of v, if that was just x, it would be 1, right? But then we have to multiply by dv dt. So we don't actually need the 1 there. It's just dv dt. Now here we've got 4/3 pi r cubed. Now 4/3 pi is a constant, so we're going to take 3 times 4/3 pi, which will just give us 4 pi. We subtract 1 from the exponent, and then we have to multiply by dr dt. Okay, now what are we given? We're given that the volume increases at a constant rate of 2 feet cubed per minute. Well, the rate of the volume is dv dt. So for dv dt, we're going to plug in 2. And we're looking for the rate of the radius, so we're looking for dr dt when the rate is 3. So here we have 2 equals, this would be 36 pi dr dt. So we would divide both sides by 36 pi. And if we wanted an approximation, we would see that dr dt is approximately 0.018 feet per minute.